Welcome to the third video in this series on thermodynamics. In the previous video, bookmarked below, we went over the historical background that led to the development of the theory of thermodynamics, from which came several definitions, including the definition of what reversibility actually is and why it's important. In this video, we'll build on that to develop the first law of thermodynamics, commonly called the conservation of energy. Previously, heat flow was seen to be defined thermodynamically as the integral of the heat capacity times the change in temperature. Work, defined as a perfect gas pushing against the piston, is the integral of minus P times the change in volume. The first law of thermodynamics specifically says the total energy of an isolated system is constant. Once again, since the universe is constant, this is sometimes stated as the energy of the universe is constant. Mathematically, that is stated as U, which is the internal energy, is equal to Q, heat, plus W, work. In other words, in the universe, heat can get exchanged with work, work can get exchanged with heat, but the total never changes and energy is conserved. So the total energy of an isolated system is heat plus work. As mentioned in previous videos, the total energy is not knowable. All you can see is the change in a system. So, the first law of dynamics states that the change in internal energy is equal to the change in heat plus the change in work. This is a universal law and is the definition of the first law. Now, it was also mentioned that thermodynamics only works on a reversible process, where a process is carried out with an infinite number of infinitely small steps. In the real world, you can approximate this by holding one variable constant. And in the universe, there aren't that many variables. You have the ideal gas law variables, pressure, volume, temperature, and the number of moles, plus heat as a variable. Also, for now, recall that the number of moles is simply a scalar. The more moles you have, the more energy you have. You double the number of moles, you double the amount of energy, you cut the number of moles in half, you get half the energy. So for now, we can simply ignore n. That leaves us with four variables. So how does the first law operate? For a reversible process, I have to keep one variable constant. So first I look at what happens if I keep the volume constant. The first law is always the first law. Delta U is heat plus work. Work is defined as minus the integral of pressure times the change in volume. So if I have a constant volume, dV is 0, the internal energy is simply equal to the heat at a constant volume. Heat is defined as the heat capacity times the change in temperature. So in this case, the internal energy is the integral of the heat capacity at a constant volume, CV, dt. This is also true, always. It's an alternate statement of the first law, with CV for an ideal monatomic gas being 3/2 times the gas constant. This alternate statement helps a lot. If I go to another condition where I do something reversibly at a constant temperature, first law says the internal energy is heat plus work. It also says it's equal to the integral of CV dt. At a constant temperature, dt is 0, so the change in internal energy is also going to be 0. If I have an adiabatic process where I hold heat constant, delta U is heat plus work. It's also equal to CV dt. If heat is constant, I am left with CV dt is simply equal to work, or CV dt is equal to minus PdV. This is going to be an important point. The integral of P dV implies that pressure is constant. You can only hold one variable constant at a time. If heat is being held constant, pressure cannot be held constant. So you have to substitute. You substitute based on the fact that you're dealing with an ideal gas, where PV equals nRT. Pressure is simply RT over V. Since the definition of the heat capacity is 3/2 R, your R's are going to cancel. Cross multiply by T, you get the integral of 3/2 1 over T dt is equal to minus 1 over V dV. 1 over x dx is the natural log, so I get 3/2 log T2 over T1 is equal to minus log V2 over V1. This solution does not give me the internal energy, it just helps me get there. I have T2, T1, V2, and V1. If I know three of these, if I know 2 volume and 1 temperature, I can find the second temperature. I can determine the value of dt, and I can find delta U. So, the internal energy is defined as heat plus work. At a constant volume, that solves as the heat capacity times the change in temperature. Because of that truth, at a constant temperature, the internal energy is going to be 0. And for an adiabatic process, you have a sort of circuitous path where first you find dt, and then you can solve for CV dt. One variable left. What happens to the internal energy at a constant pressure? The internal energy is heat plus work, or heat minus PdV. dP is 0, so I'm totally good with having pressure constant. However, what happens to Q? Another way of writing that is the heat transferred is the internal energy plus PdV. That heat is being held at a constant pressure. The heat at a constant pressure is found by taking the heat capacity at a constant pressure times the change in temperature, where for an ideal gas, the heat capacity at a constant pressure is 5/2 R. So very simply, the heat at this temperature, at this condition, would be 5/2 R T2 minus T1. T2 minus T1 is the final temperature minus the initial temperature. Or in other words, I've developed another state function, a function that only depends on where you start and where you finish. That state function is a more familiar one. It's called enthalpy. Delta H is defined as the change in heat at a constant pressure, or the integral of Cp dt. This is also always true and an alternate statement of the first law. So at a constant pressure, delta H is Cp dt. Just like the internal energy, this is always going to be true. Therefore, isothermally, since dt is 0, the enthalpy is also 0. For an adiabatic process, dq is Cp, so you get Cp dt. Therefore, to get back to the internal energy, if the internal energy is heat plus work, I have a constant pressure, the heat is the enthalpy. So the internal energy at a constant pressure is the enthalpy minus PdV. So if I know the enthalpy and I know the work, I can find the internal energy. Similarly, at a constant volume, If I know the work and I know the internal energy, the enthalpy would be the internal energy plus PdV, and that would be also always be equal to CP/dT. These are the derivations of the first law. In a separate video, you will get to see how these are implemented with worked examples. So, to finish off, we have the first law that says the energy of the universe is a constant. The energy of the universe is equal to the amount of heat plus the amount of work that is being produced. This actually says nothing about how a process happens. All it says is that heat gets turned into work and work gets turned into heat. It does not say in which direction this will go. Everybody knows, just from everyday experience, which way it will go. If you put something hot on top of something cold, the hot thing is going to get cooler, the cold thing is going to get warmer, and both will wind up at the same temperature. First law does not explain why that happens. This is scientifically and philosophically was a huge problem. A scientist called James Clerk Maxwell phrased it quite nicely. Basically, everybody knows energy flows from hot to cold. Nobody knew why. To goad his compatriots into thinking about the problem, he rather whimsically came up with the idea of Maxwell's demon, where he said, well, since this is happening, there must be a little devil inside every system that is just using his pitchfork to move heat from high to low. Obviously, we know that's not correct, and obviously Maxwell knew that was not correct. He did use this analogy to urge people to look into the problem deeper, and that would be the development of the second law. That will be discussed in a following video that is linked in the description below.